Today we're going to start looking at clustering, and I'm going to give you the general idea of what we want to do with clustering. So this is unsupervised learning, and basically we want to look at how the data is structured. So the basic idea of clustering is to try to group similar examples together. We have something like this. We can intuitively see that these points are in 3 different clouds, so we could try to put them together in this way, group them like this. So the basic idea today is going to look at a brief introduction to clustering, and then we're going to look at the k-means algorithm as a first example of clustering, and have a first look at this expectation maximization algorithm, which is very used in unsupervised learning for reasons that we're going to understand when we talk about it. So this is the basic idea, trying to find how similar examples fit together. Now, why would we want to do this? We can try to use clustering to help understand the data, to find meaningful groups in our examples, to try to reduce the amount of data that we have. For instance, sometimes this may be to help understand the data. If we have 100,000 different examples, it's very hard to deal with that. If we group them together into a dozen clusters, for example, of similar things, then it's much easier to understand what we're dealing with. We may also want to do that to improve efficiency of some algorithm that we have for supervised learning or something like that. So basically, clustering does not have clustering is, as a verb, will be to create a cluster. It does not have a very well-defined a priori objective, and we can use it for different purposes. So there are also when we use clustering for different purposes, we also need to think about what the purpose that we have, and that will dictate how we evaluate the different clusters and how we want to do the clustering. But the general idea would be to try to minimize the difference or maximize the similarity between the examples within the clusters, and maximize the distance or minimize the similarity of examples in different clusters. So we want to group things that are alike together and keep them away from things that are different. So we always need some measure of similarity or difference. It may be a distance, or in some cases we can do clustering without distance measurements. Distances have some specific properties algebraically, and we may have some indices that are not quite distances. But we always need to have some measure of similarity or difference in order to group things together that are more alike and keep them away from things that are more different. So one example of a classical example of clustering is this example of hierarchical clustering, which is Darwin's sketch of the tree of life, the way organisms can be grouped together. So we can have these small branches of species, then we have genera and families and so on, and we have higher levels of taxonomy. This is an example of hierarchical clustering because we have groups forming smaller clusters, and then groups of clusters forming larger clusters and clustering at different levels. A more recent example is this work using density-based clustering to try to identify ghost cities and ghost neighborhoods in China. So these authors used positional data from users of Baidu in China with mobile phones and so on, and they found out the internet access points, or sometimes GPS data, from many millions of users over the day, and clustering where users spend more time, they could find that there were, of course, places in cities which were mostly empty during the day, but then people returned from work and went to sleep, so they had occupancy at different times. But there were places that were empty all the time. There was no one there using internet or phone connections and so on. So they could identify several cities that had large neighborhoods which were just empty buildings, because there's been a lot of construction in China, and much more than what people are actually using. So these are some applications of clustering, basically to try to organize data to help us understand it. So another application would be to summarize data, to reduce the amount of data that we have while still representing the same kind of structure in the data. When we cluster data into prototypes, then we can use those prototypes as representatives of groups of points, and we can do this to improve the efficiency of some learning algorithm, for example, for supervised learning, or to compress data and so forth. So an example of that would be we have these initial points in blue, but we can compress the data into those red crosses while keeping the same overall shape, and we can control the amount of values that we have left. So we're going to see an example now a bit further on of doing this kind of thing. Now, the one problem that we have when clustering is that, unlike with supervised learning, we don't have the answer to look up. So you can imagine that clustering is a bit like classification, only you don't know the classes. So you only have the features, you don't know the classes, you cannot supervise the learning of the algorithm. And so this leads to some uncertainty here. For example, we could consider that in this data set we have two clusters, the red and the green. Or we could consider that we have three clusters. Maybe these four here are a bit further away from the others and could be considered another cluster, or 5 clusters, or 6 clusters. So there are many ways we could group these points into different numbers of clusters. So we usually have to do a lot of decisions when we want to do clustering, and often this requires that we understand something about the data when doing these decisions. For example, one basic decision is whether we want clustering to be partitional. We want to divide our data points into a set of groups all at the same level, so a partition of our data set, or if we want to do it hierarchically. If we want to create clusters that then belong to other clusters at a higher level and so on, like that tree of life that Darwin worked. So depending on this decision, the result will be very different. In this example, this would be an example of partitional clustering. We have 5 clusters that are all at the same level. We only have this one level where we partition our data through all the groups. But we could consider this hierarchical clustering. We have 2 levels here, one represented by the color, where we have this large group green and this red here. And then we have a lower level represented by the symbols, where the red cluster is subdivided into 3 smaller clusters, and the green cluster is subdivided into 2 smaller clusters. So this would give us a different kinds of clustering, whether we decide to do it partitionally or hierarchically. And then we also have to decide about the membership of points to each cluster. So far, we have been using an exclusive membership. So if one point belongs to the red square, it only belongs to the red square and doesn't belong to anything else. But we could do it in other way. We could have overlapping clusters where points can belong to different clusters, or this also happens in hierarchical clusters, because in fact if you have a point belonging to a smaller cluster, that cluster also belongs to a larger cluster, so the point is in fact in several clusters here. But we can do fuzzy clustering. In fuzzy logic, we have a membership function that is a continuous value between 0 and 1, and which specifies how much one point belongs to a set. So for example, suppose that we wanted to cluster temperatures into cold, warm, and hot. There is no rigorous definition about when cold becomes warm or when warm becomes hot. So we could talk about temperatures like 20 degrees, they are, say, 60% warm and maybe 50% cold and 2% hot or something like that, and we could manage these membership values in a continuous way. If we impose a restriction that these membership values must integrate to 1, we can have a probability function or a probability distribution for the membership of each point. And in this case, we have probabilistic clustering. So probabilistic clustering also assigns points to clusters in a continuous manner. It's not a either-or function, but these values are a probability. So the probability of belonging somewhere must add up to 1 because the point must go somewhere. Also, we can decide on the coverage of examples. So we may want to make sure that all our examples belong to some cluster, or we may want to create clusters that exclude some examples, as noise, for example, and they don't belong to any cluster. So in that case, we have to decide whether we want complete clustering or partial clustering. So apart from these decisions, we also have some features of the clusters themselves. For example, because of the data, clusters can be well separated, in which case we have points that are always more similar to points within the cluster than to points outside the cluster. Or they may be, we may create clusters by using prototypes. Usually with well-separated clusters, prototype-based clusters work well, where we choose one point to represent the whole group. So each cluster has one representative example, which may belong to our data set, or it may be a different example. We may create one synthetically. We also have another idea of clustering, which is contiguity-based. So we group together points not because they are all similar to each other, but because there is some contiguous region that joins, for example, this point here in the same cluster as this one here, and not to the other ones that are actually closer together. So we can think of clusters in different ways, whether they are blobs of things that are very similar to each other, or some continuous regions where there is a path that goes through similar examples, and so on. Another possibility is to use density-based clustering. So regions with high density belong to clusters, and then regions with very low density are just noise and they are discarded. So in this case, we have 3 clusters, red, green, and blue, and then these black dots here do not belong to any cluster, and this is an example of a partial coverage. So we do not force all points to belong to clusters. So how do we compare these different examples? There are some possibilities. We can use similarity. We need to use similarity measures, but we can have many different ones, many different similarity measures. We also need to decide how the points are related to the clusters, if they belong fully to the cluster, partially, if not all points belong to the cluster, or if the coverage is complete. And we also need to decide how to create a cluster. So usually, as you can imagine, depending on the data, these answers can be right or wrong differently, depending on the data set that you're using. So it's generally useful to try different approaches and to try to understand the data, visualize the data, and so on, in order to find out which is the best way of clustering your data. And the goal in general is to try to extract some information about the data. Remember that in unsupervised learning, we do not have one specific criteria where we can measure the performance of our learner, our models, but we want to use unsupervised learning to transform the data into something that is more useful. So generally, it's that outcome that we need to evaluate depending on what we want to use that data for. So let's see an example of clustering. This is k-means clustering. It's often referred to as the k-means algorithm, although in fact there are different algorithms, and the one I'm going to talk about is the classical Lloyd's algorithm for computing k-means. But the idea here is that we define from the start how many clusters we want to be in the clustering, in the set of clusters. So this is the k value there. We want k clusters. And then we define each cluster as the set of points that is closest to the representative vector for that cluster. So this is the mean of the cluster, usually. The number of centroids, and thus the number of clusters, is that k parameter. And this is a partitional cluster. It's all at the same level. It's exclusive. Each point belongs only to one cluster, and there is complete coverage. So there are no points that are left outside the cluster. Also, each cluster is defined by a prototype, so this is prototype-based clustering. The algorithm consists of starting with a random set of centroids of these prototypes, then assigning all the points in our data to the cluster corresponding to the nearest of the centroids, and then moving the centroids to the mean of all the points in the cluster. And we repeat that until convergence. So let's see two ways of starting the algorithm. One, this is by a method proposed by Forgy, is to select a random set of our examples. Note that the centroids are not examples. We move the centroids independently of the examples. But we will start with the centroids placed at randomly chosen examples. For example, like this. And now we create clusters by assigning each point to the closest centroid. So this is the first iteration where we create the first set of clusters. Another way of starting the algorithm would be this random partition, which is to assign at random each point to one of the k clusters, and then compute the centroids to be the mean of each of these random clusters. So in this initialization, the centroids tend to be more close to the center of the data that we have, because we are averaging over a random set of points. So let's see how the algorithm works. We have this original data. We don't have labels for the data, so we're going to try to figure out which clusters we should place these points into. And we begin by initializing with the Forgy method by choosing at random a set of points and then assigning the data to each of these centroids, so to each of these clusters. And now what we're going to do is to compute the mean point for each of the clusters. So we've assigned all these blue squares to these blue square centroids, and now we're going to average all the coordinates and compute the mean point for these. So this would be the new place of this centroid here, this prototype. We're going to do the same for all the other centroids. So now we have the centroids in different places. We need to recompute the clusters, because now, since the centroids moved, points may no longer be closer to one of them, they may be closer to the other. So we recompute the clusters, and now the mean point of the clusters will be again different, because now there are different sets of points in the cluster. So we compute the mean point again, we move the centroid, we recompute the clusters, and we do that iteratively, and we do that until convergence. So eventually we are no longer moving, there are no changes in the cluster, so there are no changes in the mean, and our centroids remain in the same place. So this is how the k-mean algorithm, Lloyd's algorithm, works for computing k-mean. This is easy to implement, although you don't need to implement, but just to recapitulate the algorithm. We need to find the closest centroid. So basically we have a matrix with the coordinates of all those centroids, and we have a matrix with the coordinates of our data points. And what we're going to do is, for each of our data points, we're going to compute the distance to all the centroids, and then we're going to find the one which has the minimum distance. And this will be the label assigned to that data point. So each data point will be labeled with the index of the centroid that is closest to it. And now we need to compute the new coordinates of each centroid. So we're going to go through all the data, and we're going to find which of the data points is closest to our centroid, and then we're going to, for each of the centroids, we're going to compute the mean value of all the data points that belong to that cluster. And this will be the new coordinates for the centroid. The two ways of initializing this can be, two examples of initialization can be Forgy, which basically we select a random sample of the indices of our data points. We have this range spanning all our data. We shuffle it and we take the first k value. So we assign centroids to a random set of different data points. Note that this way we ensure that we do not assign two centroids to the exact exact same data point. We are sampling with, without preposition here. Random partition simply assigns random values to the labels, to the cluster labels for all our points, and then computes the centroids for each of these random clusters. Now, in general, we can often we use Euclidean distance. In this example, I use Euclidean distance. It's easier also to visualize. But in general, you can find you can use any distance measure for k-means. So as long as you're able to compute some similarity to the point, but then also able to compute the mean value for your coordinates, then you can use k-means. And conceptually, you can imagine that it's similar to a self-organizing map that we saw last week, only we don't have that two-dimensional topology also. So it would be like a self-organizing map, but only with the neurons disconnected from one another, so they can spread out through the data space, but they don't drag each other along. However, there is one problem with k-means, is that we need to be able to compute the mean. This is easy to do when we are dealing with coordinates, for example, because if we have a set of points, we can find the midpoint of that set. But you cannot do if you're comparing, for example, text documents. You can measure a difference between two text documents by, say, counting the words and seeing how many words are different or something like that. But it's not easy to think about what would be the average text document. So if you have two text documents, what is the mean text document of the two? Because you don't have mean words or something like that. So in that case, we can use a variant of k-means, similar to k-means, but it's called k-medoids, in which the prototype is always a data point. It's not an average, it's not a mean of the data points, but it's one of the points in our data set. And all we need is some kind of difference or similarity measure. So what we do in this case, we we do the same kind of assignment. We assign each example to the cluster corresponding to the medoid that is most similar to that data point. But then the way we update the prototype is to, for each of these clusters, scan all the points that belong to the cluster and try to find a new point that is more in the center of the cluster. And that can be defined, for example, by summing all the distances or some measure like that. So we are not moving the centroids by computing the means, but we are changing the medoids by trying to find another example that would be closer to all the others in the cluster. And apart from that, the algorithm goes in the same way. So this brings us to one very fundamental algorithm that is used in lots of cases in unsupervised learning, which is this expectation maximization algorithm. The idea here is that we have a set of observed data, or I'm going to call it X, and we also have these missing or latent variables, which is part of the data, but it's something that we don't know. So this could be, for example, which cluster each point belongs to. Note that in supervised learning, we would know X and Z. We even called it Y, because that was what we were trying to predict, but it would be the class labels, and X would be the set of features. Now here, this Z parameter, this Z set of data is something we don't know. We don't know, for example, which cluster each point belongs to. And we have this set of parameters, for example, the coordinates of the centroids, that we want to optimize, that we want to find. And we want to find them usually by maximizing the likelihood. So the likelihood would be, for our parameters, would be the probability of finding that kind of data, that dispersion of data, if our parameters are correct. So we want to maximize that. This is what we do with supervised learning, basically. We have the features, we have the classes, for example, or the epsilon values for a regression, and we want to find the parameters that maximize that probability. However, in unsupervised learning, in clustering, we don't have part of that information. We don't have the V, which would be the assignment to each group. So what we need to do is we need to try to find this data in some way, because this would be the complete data if we knew which were the clusters the points belong to, but actually we only have this part. So we need to do something about this unknown that we have here. Since we don't know the z value, we cannot do this directly. We cannot compute directly or maximize the likelihood of our parameters without some estimate of that z value. But we can have an estimate of these z values if we assume some values for the parameters, because in that case we know the parameters. For example, we know where the centroids are, or we guess where the centroids are. We know how the points are distributed, and now we can try to find what would be the expected value of those z latent variables. So the assignment, for example, of a point to a cluster. And this is the expectation maximization algorithm. The first part is we need to create this likelihood function that we can maximize, but we are missing a part of it, which is the z value. So we compute the expected values for these z variables by using a first guess of our parameters. So if we look at k-means, for example, we can look at the position of the centroids, and this gives us an idea of, if those positions are correct, which group, which cluster each point should belong to. Note that k-means is not exactly an expectation maximization, an example of expectation maximization, because we do not compute the probability of each point belonging to a cluster, we simply assign it to a cluster. But in any case, we have this estimate of which cluster each point belongs to. And if we know which cluster each point belongs to, then we can write the likelihood function, which involves the assignment of the points to the cluster, and also the distribution of x as a function of our parameters. So now we can change our parameters and maximize this likelihood function. And this is the maximization step. So first we fill in the gaps in our likelihood function by estimating the z values from a previous guess of our parameters, and then we adjust our parameters by maximizing the likelihood of using that expression. And now we repeat this going back and forth between the two. After we optimize the parameters, we have a new, better guess for our parameters. We can recompute the estimate of those latent variables, and then go back to maximizing the likelihood, and so on. So we can also imagine this as a sort of maximization or alternating optimization, in that we are trying to optimize with respect to those hidden variables and then optimize with respect to our parameters and jumping back and forth. So this is what we can imagine doing in k-means, where we can think of this distortion measure, which would be the quadratic distance between points inside the same cluster. So this is a variable that tells us if the points belong to that cluster or not. And now we measure the distance between each point and the centroid of the cluster. So this way we have a notion of how dispersed the points are around the centroid. And we only do that for those points that belong to that cluster. But to do this, to compute this, we need to know which points belong to which cluster. So we want to minimize this distortion measure, but we need to know which points belong to the cluster. So we use an estimate of the centroids to find out where the points should belong to in order to minimize this measure. And then we change the centers of the cluster using those assignments in order to keep minimizing the measure, and we jump back and forth between the two. So this is similar to expectation maximization, with the only difference that these variables here are only 0 or 1 and not the actual averages, not the expected values of those z's. And this ends up tending towards the logarithmic likelihood of the distribution of the variables. So actually, it is similar to what we found when maximizing the likelihood in the linear regression case, where we also found these quadratic distances. So basically, k-means is almost expectation maximization. Tem alguma dúvida? K-means is almost expectation maximization. The only difference is that we are not using probability distributions or estimating probabilities for the latent variables, but we are estimating the cluster assignments from the centroids and then recomputing the centroids from those assignments and then recomputing the assignments and going back and forth. We're going to see a bit more of this when we talk about Gaussian mixtures, which is another way of doing clustering, and there we'll be actually using fully the expectation maximization algorithm. Now let's see an application of k-means. This is one common application of k-means. It's even the original application of k-means. It's for vector quantization. This means this is a technique for reducing the amount of data you have when you have continuous values, vectors of continuous values, and you want to quantize them or discretize them into a subset of fixed values. So we're going to use k-means to quantize the color values of an image. This is an image you can find in Wikipedia. It's an example for k-means, and I'm also following a bit this scikit-learn demo that then you can look at if you want. So this is the image. The good thing about this image for this kind of demonstration is that it doesn't have a blue channel. So it only has mixtures of red and green. So we can represent the pixels of this image in a two-dimensional chart by representing the value of the red channel and the green channel, and these are the pixels in the image. So to process the image, we can use scikit image. We have these image save and image read functions. We read the image file, and this results in a matrix like a NumPy matrix for this file. So we have a three-dimensional matrix because we have width, height, and then we have three layers for red, green, and blue channels. Now we can reshape our image. I'm dividing by 255, so all the color levels are between 0 and 1, and I'm reshaping it so that we have the three channels, the three color channels in three columns, and then as many rows as there are pixels in the image. So the number of pixels is width multiplied by height, and the number of columns is the three color channels that we have. Now we can throw away blue. We'll keep only the two first columns, and we can plot the pixel colors by using the actual colors we took from the image. So if you use a scatter plot, you can specify a color as a red, green, blue tuple for each of the pixels that you want to draw. So this is how you can do this plot. And now we have the red and green components in a matrix, and we can do k-means clustering in those two dimensions to find the k-means for this data set. We can use 64 centroids, for example. This would be the distribution, and this is how we can do that. This is the number of centroids that we want to use. We create a k-means clustering object, and we fit it with our columns with all the pixels. So now we use the prediction to get the labels for each of our points, and we know where the centroids are. So we can find the cluster centroids, and we can mark them with an X. So basically this is what happened here. I used the k-means object to compute the 64 centroids, and then find the labels for the points, but also to plot where the centroids are. And as you can see, the centroids are distributed according to the density of the points here. So the more points there are in some region, there's more centroids around there. If you don't have points here, there are no centroids here. Here it's also very sparsely populated. So all points belong to some cluster, but the centroids are distributed according to the distribution of points. And now we can use these, after computing the k-means, we can convert the color value of all points in one cluster to the color of the centroid, so that all our points will only have 64 different colors. This is easy to do. We have the labels for all the colors, So we can go for each of our metrics of the different pixels. For each of these, we find the label. Using the label, we get the centroid values, and since the centroids are coordinates in red and green color space, we simply assign that to the color. So each of our pixels will get the color corresponding to the centroid that is close to it. And so this is what happens. We can then save the image, and this is what happens to the image. This one initially had, it actually had it's 24 bits in file. It's actually only 16 since we are not using glue, but we reduced that to 6 bits. So this is only 64 colors in total, and you see that there is not a very big difference in the image. We can do this a bit more drastically. Let's use only 8 centroids. This is where they are distributed. Now we assign each pixel, we give it the color of the centroid it belongs to. So these are the 8 colors that we're going to use, and we can then replace that in the image. And now we can notice some change in the image, but it's still similar to the original. The difference is that now this one is only 3 bits because we only have 8 different colors there. So to sum up, we saw the idea of clustering, of grouping examples by similarity, and we saw different decisions that we have to take. We did not see yet examples of different clustering algorithms, only k-means, but these decisions that you have to make will depend strongly on what the data is like and what your similarity measures are like. So we have to decide how we're going to do the clustering and how the points will belong to the clusters, and also we have to think about the kinds of clusters that we want to make. All of this is very dependent on the data. So as you can imagine, you have different algorithms that are appropriate to different kinds of data. We saw also the k-means algorithm, and we took a first look at the expectation maximization algorithm, which we are going to revisit both in Gaussian mixtures and also in hidden Markov models when we talk later on.